be heard. I'm using these mics. Okay, I think I am. Good. Okay, so the primary goal of this particular paper is to look at sort of the informal way that we analyze algorithms. Right, given some sort of a functional program, we tend to sort of, especially when we're teaching, say, undergraduates, right, we look at the algorithm, we basically write down a function on the board that looks a lot like the algorithm, more or less, right? It's supposed to represent the cost in terms of the size of the input, right? And that's what we'll call cost recurrence. So we write that down, and then we go ahead and we solve it or come up with some sort of a closed form, et cetera. And so the goal here that I want to talk about is to try to really sort of use denotational semantics to give a formal account of that sort of informal process of coming up with that cost recurrence. Not focusing on solving it directly, just the actual coming up with that recurrence. Where does it actually come from? And just to be clear, right, to sort of set a line on that, not so much focusing on effectively building a better mousetrap, not trying to come up with techniques for more PL-based approaches to cost analysis like ARA and other approaches. Really just want to focus on giving a formal account of that informal process. And so the big picture here, starting off with some sort of a source language, which for right now is just a call-by-value version of ML. With just data types and fold, we handle general recursion in other papers. But that's our basic source language that we're working with. So there's a syntactic part where we do sort of a translation into the writer monad to get what we call a syntactic recurrence, and that's basically now call by name predicative polymorphism. I should have said when I think of call by name ML or call by value ML, that's with let-polymorphism. So extract that into some form of a predicative polymorphic lambda calculus. And then hit it with a model, interpret the recurrence in some sort of a denotational semantics. That's where we give this notion of size for the arguments of the original source program. And it's at that point where we should start seeing these recurrences that we would expect to see showing up. All right, and so as an example here, right, so let's consider, say, a typical program for, say, like binary search tree membership testing, right, which is basically a tree fold, as shown here. And let's sort of focus right now just on counting, say, the number of recursive calls that are induced by that fold, right? So that's the program that we're starting with, right? The goal is to come up with the recurrence you would expect to see when doing a cost analysis for this. And so the first step is that translation into the writer monad, which then translates a program of type sigma into a new program of type what I'll call cost and the potential of sigma. So that's type C there is a cost type, which in the syntax is basically just a type, but will generally be interpreted by numbers or something like that. And then that potential sigma is what is the other part there. And that's what we think of as the type of potentials or sizes or usage costs of values of type sigma in the original source language. All right, so size is the right way to think about it. Potential is a term that a co-author Jim Royer and I adopted a long time ago and possibly really poorly. So just to clarify, it does not directly have anything to do with potentials in amortized analysis. Now we're really thinking of that as potential cost of a value of type sigma. How might it get used and contribute to cost? And so in this case, this since costs are really sort of explicit in this syntax here, we call that pair a complexity. But in the notation here, I'll use this sort of E with cost as being the pair because I find it a little bit easier to read, right? And when you look at this, right, this is basically the what you would expect as the cost, the translation you would get from that binary search tree membership program, right? Which is again a tree fold. And in this case, say you've got a node, well, then what are you going to do, right? You're going to compare the two values again, and if, say, the comparison comes out less than, right, the cost, right, the result is going to be basically the potential of the left-hand recursive call. That's that R0, that's that recursive call there. The P and the C subscripts are basically the projections on these pairs. And the cost is then 1 for the cost of the recursive function, right, for making that recursive call, the cost of the comparison, along with the cost of one more cost for actually this particular unfolding of the fold. And so where this gets interesting is then when we interpret that syntactic recurrence in a model. right? And so in this case, right, if say the goal is to analyze that binary search tree membership function in terms of the height of the argument tree in the first place, right, we want a model where we are essentially interpreting trees by their height. And so in that case, we'd interpret the tree type by the natural numbers or some version thereof. We'd interpret the empty constructor by 0 and the node constructor as just adding 1 to the maximum of the interpretations of the subtrees. Right, and that gives us an interpretation of trees where every tree is now interpreted by its height. And so doing that, right, we still have to interpret fold as well in this model. And in this case, right, so essentially interpreting fold over a height now, right, because the tree argument is actually just a number, right? And so interpreting over the height is essentially a maximum over the branches, where we have to take that maximum for the node branch, right, over sort of in some sense all of the possible heights that one might encounter for the subtrees of a tree of height h, right? And hence that's where that h0 max h1 is less than h coming through for that overall maximum. You'll also notice that what do we do about that label? Well, in effect, if the relevant notion of size for our trees is just the height of the tree, the labels are irrelevant, right? And so, in fact, it ends up working to come up with semantics where we basically say, well, let's set that label value to essentially an infinite value. That infinity comes out of the fact that when you sort of dig into the details of defining these models, it's actually very convenient to interpret all the types as complete lattices. So there is a top element, an infinity. And so in this case, we're basically saying, I don't care about the size of the labels. Or more accurately, I'm going to do this interpretation when the label has size at most infinitely large, which could be anything. And so when we do that, then, in fact, the interpretation of the original recurrence back here, right, when we interpret this, we get, in fact, pretty much exactly the recurrence you would expect to get by looking at the original source program and staring at it hard and say, what will we get as a recurrence if we want to describe the cost of this program in terms of the height of the tree, right? And if you're looking at some tree of arbitrary height h, you're going to have to more or less maximize over all of the possible subtrees that have height smaller than h, which is exactly what that recurrence is there. And so this is sort of giving the idea, the flavor of what we'd expect to be coming out of this sort of a program. Okay. So that's the basic structure. And so for all this to fly, right, of course, we need a theorem that ties all of this together. And what does that boil down to? And so we start off doing that syntactic translation, which is these vertical bars. And we're basically saying then is that a bound on the denotation of the syntactic extraction of the original program. Someone has to be a bound on the original cost of the program E. And so we break that into two steps, one involving a logical relation that relates programs in the source language to syntactic recurrences in the syntactic recurrence language, right? And that particular relation, right, and then you prove the fundamental theorem, and as a consequence, the definition of that logical relation tells you that the cost component of the extracted syntactic recurrence is, in fact, a bound on the operational cost from the source programming language. Right? And then there's also a bound related to the result that you get. That bound then is defined in terms of a notion of a size order in the recurrence language itself. Right? And then you prove that you actually have a model of the recurrence language. And those two together then glue together to tell you that the semantic recurrence you extract that looks like what we normally see on the board actually gives a bound on the original program, the cost, and as it turns, the cost of the original program, as well as it turns out, the size of the result. So that size order, that's what we actually use to axiomatize that recurrence language rather than equations. It's axiomatized by a size ordering. And so the axioms on that size order tend to come in a couple of flavors. Some of them have to do with how the introductory and elimination forms for each type interact with each other. And the others have to do with monotonicity of the size order. And so those first kinds that are actually, to me, a little bit interesting, that's where you actually start seeing things look a lot like Galois connections coming up there. And so they basically end up playing the role of saying that the introduction form for a type for any given type essentially looks a lot like the abstraction function you would see in a Galois connection, whereas the elimination form ends up looking a lot like the concretization function. Yeah, and that sort of makes sense when you think about it, because the whole point here is that you're really sort of trying to abstract away information about the original values in terms of the size. Sizes are sort of abstract descriptions of your original values. All right, and so then really the thing that I want to talk a little bit about, right, are the various kinds of models. So the one that I was just talking about, we might call the main constructor model, basically is for each data type just counting up the number of main constructors in a value of that type, all right? And so how you count those up, right, maybe you can count up total numbers, or there's the example I gave where you're basically looking at a parse tree and counting sort of maximum depth of constructors. Right, and so that's one where you interpret nat tree as n, and when I say n here, what I really mean is n with a top, natural numbers with a top, so you have an infinity element to make things to just be able to always take these maximums that show up in the definitions of in the interpretation of fold. That's all well and fine, but if you are, say, have in front of you a function, say, that takes a nat labeled tree and it adds up all of the nats on all of the labels, to give you a result, summing all of those values up, you're going to actually run into trouble with this model. Now, not trouble in that it's going to give you the wrong result. It's a perfectly fine model if it's actually a model of the recurrence language, and the semantic recurrence in its solution, right, is going to be a bound. Almost by definition, or at least by the theorems. The problem is that in that particular setting, what you get is a bound of infinity for the cost, which is say, yes, your program runs and its cost is at most infinite. And the results, as it turns out, will also have a bound of infinity. Yes, you do get a result and the size is at most infinite, which is true, not necessarily most useful information you might want. Right, but you can define more complex models where, for example, you can count all of the constructors of all of the data types individually, right? So you interpret really every single data type as a function that maps all data types numbers, with the intent being that the interpretation, say, of a value of type nat tree maps nat to, say, the nat inductive type to the maximum label size, where and the number of nat tree, maps nat tree itself, say, to the number of nodes, tree nodes, right? And when you do that, all right, you also, of course, have to interpret fold, and that's where sort of the pain comes in. But fold comes up with a fairly similar looking kind of interpretation. That big maximum that we had seen previously for heights here now ends up being a big maximum over, well, our values are sort of these point-wise counters for all possible data types, and you end up maximizing over sort of all point-wise smaller things. All right, so it's a little bit painful to look at, but nonetheless, you end up getting then, say, if you're looking at something like summing up the labels on a nat tree, you end up getting the exact same recurrence that you would expect when you sort of write these down informally. All right. On the other hand, that's sort of a bit of an annoyance, having that additional complexity if you do actually want to analyze functions that don't depend on the labels, right? Because now you're sort of having to worry, and especially in terms of the computation of that fold, you have to worry about all of that extra information the way the fold is defined. And that comes up in particular with polymorphic functions, right? Where, in fact, your typical polymorphic function, I'm going to switch to lists instead of trees now, but right, intuitively at least, right, should not depend on the labels at all. And so what's going on there, right, is that in the model, both of the two previous models that I've talked about, the interpretation of the universal quantifier is sort of the standard one. We just take a product over all of the unquantified types, keeping in mind this is all predicative, so there's no real problem doing that. All right, but that means then if you're looking at that all constructor model, when you want to reason about even just a polymorphic function, you sort of have to, at least technically, you have to instantiate it first at a type to reason about the corresponding recurrence of that type. And what that means then is you're computing fold now over these rather complex point-wise descriptions of how many constructors you have at every single data type. And what we'd really like is what we do informally when we say analyze a polymorphic list function, which say we're just going to analyze this in terms of the length of the list, right? It should be a function from numbers to numbers, even though we know we might have complex element types in any particular instantiation. And I'll just point out, right, that n arrow n there looks very similar. It's not quite, but it's very close to the standard interpretation of the quantifier, of the universal quantifier you would get from that main constructor counting model. There'd be an extra indexing over all of the small types, but for every single type, since you're just counting the number of main constructors, you would get numbers to numbers as the actual type. And so we actually can do that, right? It's another model. And in this case, this is a model where we can sort of merge them and we can leverage those Galois connection between the non-quantified types of the main constructor and the all constructor models, right? Again, you can think of just counting the number of main constructors as basically being essentially an abstract form of counting, more abstract presentation than counting all of the constructors. But we can leverage that to get a non-standard interpretation of the universal constructor, right? In which case, what we get now is that the small types are all interpreted with this very fine-grained information that describe all the possible types, all the possible uses of all the constructors. But the quantified types, right, are just interpreted using main constructors. And so in that case, what ends up happening now is that, for example, you really only have to consider examining folds now at concretizations of numbers, because we are now going to essentially say, okay, the value of, if we're interpreting or analyzing a function of type alpha list to alpha list, right, the alpha list is going to be interpreted by a value of type n in this model of type nat, right? We have to then concretize that, but that ends up being just one of these pointwise counting of everything again, but one where in fact only the nat list type gets mapped to n, the number of cons constructors, essentially. Everything else gets mapped to infinity to say anything else that's showing up in that list, you can treat as having a trivial bound on the size. Why is that? Well, it's because it was a polymorphic function in the first place. And so when we do that, then, for example, if we say take polymorphic reverse, like the linear time higher order reverse function, right? What you end up with is, again, exactly the recurrences you expect when you're analyzing that informally, just by presupposing that it only depends on the length of the list. So that's the basic stuff. There's other stuff in the paper, and we're continuing to do some more ongoing work with that. Sort of the thing that I've got a bit of a bee in my bonnet right now is taking the same approach to understanding algorithms where we reason a lot more abstractly, right? Think something like analyzing heap sort, where you basically just start off saying, well, I'm going to sort a list just assuming I have, say, a log time heap implementation. And then I can analyze the sorting algorithm based on that without thinking about the heap implementation. At the same time, I then have to go off and analyze some heap implementation and reason about that separately. All right, but that's where I'll stop, and I'd be happy to take questions.
Thank you.